Good morning, Gabriele.
Good morning. Good morning, Tino. How are you?
Good. I'm doing fine. And you?
Thanks, I'm fine. Good.
See
Ready
that.
for the webinar?
And good morning to all our attendees or participants. I see they are coming in great mass. There are lots of people coming in. So give them a few minutes to settle down, and then we will present them our topic of today. You can decide when we'll start or not. According to the numbers, they are still coming in. So
yeah, I can see that. People are coming in. That's good.
All right, Gabriele, it looks like majority is probably there.
Okay, so we can start maybe.
Yes, please. I'll just go to the slides.
So, hello, first of all, and welcome to everybody to this webinar about de-energized to trade versus energized to activate. This is one of many topics that we cover during this kind of events, and considering the good feedback that we received so far from the participants, we continue sharing our knowledge regarding intrinsic safety and especially functional safety. A brief introduction about myself. I'm Gabriele Caglio. I'm the technical support specialist here at GMI, and we have Tino van de Capelle, which is the expert and today's main speaker. I would like to start with a brief introduction of GMI, for who doesn't know us. GMI is an Italian company providing field interfaces related to intrinsic safety and functional safety. This means that it's possible to find GMI devices in many industrial packages, such as DCS, ESD, fire and gas, and so on. As you can see from the screen, we are talking about oil and gas, petrochemical, pharmaceutical, mining, but also food and beverage and many other industries. We have 40 years of experience in the field. The headquarters, as I said, is in Italy, where we have our main facility and where we design, produce, and test all our products. As you can see here, we have also several offices and resellers all around the globe, so we are available and close to our end user and customer pretty much everywhere. As I mentioned before, we are a safety company. Next slide. Yes. And we aim to provide safety and reduce the risk of hazardous event to safeguard people, assets, infrastructures, production processes, of course, and the environment too. For this reason, the quality aspect of our products cannot be overlooked. We design our product, we manufacture and test 100% of our devices internally, meaning that we do not outsource any of these tasks. This is why we are confident about the quality of our devices. Couple of quick more slides before to get to the real part of the webinar. One is about the certificates that we have, or at least the certification bodies that we are dealing with. This guarantees the quality of the device, but also guarantees that GMI comply the market requirement according to the local regulation. A brief overview of our portfolio. As I mentioned, we have intrinsically safe barrier, safety relays, SEAL certified, with and without light monitoring for energized to safe and de-energized to safe application, isolators, AX power supply systems up to SEAL 3, temperature and digital multiplexer for Zone 1 installation. We also have customized termination board for an easy connection to the main PLC and DCS system. We have hard multiplexers and surge arrestors. As you can see from the slide, now we have the new X1 series. And we also provide, last but not least, consultancy, and we share our experience through courses related to functional safety and intrinsic safety. The final slide is a list of customers, which we stretch from system vendors to EPC, OEM to end user. Last thing before to start the webinar, this webinar is recorded, and in a few days you will find it available on YouTube. Subscribe, of course, if you want to get a notification. You will get a link to download the PDF copy of this presentation, or also in a couple of days from now. You will get the certificate, but only if you attend at least at 70% of the webinar. And of course, if you have any question during the presentation, write them down in the Q&A section, and we will try to answer to all of them during or at the end of the training. And I think it's all. So please, Tino, it's your
Thank
time.
you. Thank you, Gabriele. You're always very efficient. When previous people told me we will do a quick introduction, it will only take 5 minutes, it took them 10 to 15 minutes, but yours is inside the 5 minutes barrier. So well done. Okay.
Thank you.
Topic today is de-energized versus energized. To give you an idea about de-energized, if anyone watched the news a couple of days ago in Spain and in Portugal, that's a de-energized state. The question is, can some systems go to safe position when you lose your energy? And that's one of the topics that you have to consider. So what we will discuss today are some fundamental basics, and those who are involved in safety instrumented systems, majority of all the, let's say, emergency shutdown systems are always de-energized to trip. That means we are removing the energy, we are removing the instrument there, we are removing the power to the field devices, and we are hoping that the device itself will be able to go into a process safe state. With the, let's say, underlining the word, we are hoping it will be able to go to a safe state. Because as we all know, if you don't move some final elements often, they are typically stuck in the wrong state. That means even though you depressurize or you're trying to vent the instrument there, maybe the valve is mechanically stuck and stays open in the last position, which is typically in the process condition and not the safe state. Every single safety function itself, as per the IEC 61511, shall be specified in a very clear manner that every engineer that needs to build it, needs to maintain it, and foremost needs to operate it, knows exactly what the safety function is supposed to do. That's why we're always referring to this document called the SRS, and the SRS is called the Safety Requirement Specification. And those of you who are familiar with the edition 2 of the 61511, and it's both the ISA 61511 or the IEC 61511 edition 2, has today, in the current release, 29 bullets which are normative to be described. The standard is clearly saying that every safety instrumented function shall describe and shall include, but then the word, as you can see here where I'm hovering here with my cursor, the standard is saying as applicable. So a creative engineer typically will say N.A. means not applicable, in the hope that then he doesn't have to describe what the safety functionality exactly needs to be built of. So one of the topics in there is called the requirements related to energize or to de-energize to trip for each SIF. Personally, of course, I'm not longer on the committee of the 61511. I'm just observing, I'm using the text that they have been writing. I don't like the word to call it energize to trip. Because when you start a deluge system in a fire and gas application, and then you tell the engineer, we will start the engine to trip it, that doesn't sound very clear to me. But maybe I am too much an engine nerd here, and I should simplify things. So what we will do here in our webinar today is we will clearly call it de-energized to trip, which is the real item of 99% of all the safety loops, versus energized to activate. We don't call it energized to trip, we call it energized to activate, as you have to provide power to do something or to achieve your safety functionality. Start off with the basic normal one, or the, let's say, the majority of your safety loops are classically in a de-energized to trip, which here we abbreviated this with a DTT for de-energized to trip. The majority of all the loops classically are built in a de-energized to trip. Simply speaking, when I would cut the cable or I'm losing the power, well, the instrument on the other side will lose the power and is supposed to go to a safe state. If you think about a solenoid, if you think about a spring return actuator, that if you remove the instrument there, providing the vent is not blocked and the air can still vent, then the spring should have torque enough or power enough to actually move the valve to go into a closed position. The definition of trip to achieve the safe state of a sieve, that is a topic that we would like to discuss. And if you look into the standard, and I'm now referring to the IEC 61508, we will call a de-energized to trip functionality a fail-safe principle. That means you remove the power, you remove the energy, and the system is supposed to go into a safe position. Common examples of subsystems that transition the system into a safe state are, of course, shutdown or emergency shutdown or trip systems, as we mentioned already. And I start here with a simple example of a safety instrumented function. So we go from left to right. And as you can see here, we have different subsystems, providing that here the first sensor is to measure your process value in your field. You go through one of the isolators here from GMI to fed into an analog input board of a logic solver. Inside the logic solver, you will write your application program with the condition that whatever value the sensor is recognizing, whatever action needs to be taken care of. The output of the digital output module from some PLC vendors will not have power or not have current enough enabled to power the field. So therefore you will have to go over a interposing relay. And that's again an interposing relay that we'll use also in the example in our slides from GM International to interface with whatever load is connected to the final element. Then we go to subsystem number 5, which is typically your solenoid. And on the last subsystem number 6, that is classically your final element. And the final element is classically where majority of all the failures will be in your safety loops. By statistics, based on the industry statistics, 50% of all the failures in your safety loops are always between subsystem 5 and 6. In other words, the focus is clearly at the end of your safety loop. And opposite logic, if you think about it, your sensors may be built in a 1 out of 2 or in a 2 out of 3. Preferably, you would have a 2 out of 3. That means you can also maintain safety and maintain your process availability. That means that a spurious trip, one of the sensors would not trip your entire site, or one danger failure in the other transmitter would not make your system unsafe. So you have 2 out of 3 sensors here on subsystem number 1. You will have to go through 3 independent isolators. You will have to go through 3 independent channels. But then if you think about that, classically what people will do, they will move this into a single output to a single valve and to a single final element. And if you then ask him, how easy can you test in terms of proof testing your safety loops? We all know that we can easily test subsystem 1, 2, 3, often even subsystem 4 without shutting down the production. But if you have only one single valve, you cannot proof test it. And the reason why they only put one single valve is because it's costing them money. And they say, let's stick with one valve. And if you think about that, the redundancy on all the front end are all systems we can test. Some of the systems even have diagnostics. Those who have nothing that can hardly be ever tested without shutting down are only built in a 1 out of 1. So it's just like the opposite logic that we are using or that we are recognizing in our industry. I'm just seeing one question coming in. Let me quickly read this. Let me read out loud the question. Always there is debate if a design is done to de-energize to trip. Why one need the SIS safety system to be fire resistant? Since systems is fail safe, what is your thoughts on that? Well, I wish I would understand the question. Let me read it again. Maybe I read it too quick. Always there is debate if a design is done de-energize to trip. Okay, until here I fully understand what your question is. Why one need the SIS safety system to be fire resistant? And in the meantime, the same person answered fire resistant cables. Okay, let me try to think out loud. So you probably try to think of a item that there is a fire in the site. It is burning some cables. The cable is losing the power. Okay, I can see where you're coming from, but maybe on some instruments, you may need the power for a certain period enabled to go a safe state. In other words, it's not because you're turning off the power that your entire site is all of a sudden safe. You may have still some duration of time needed. That is why I'm thinking out loud now that there are some shutdown valves, maybe with an air buffer, that the air buffer needs to be there and able to go to a certain position before they said, now we are in a safe state. Or maybe some of the instruments, like an MOV as an example, would need the power to move to a position before it can say, now it's moving to a position, we can turn off the power. So there's always some, it's not like a black and white question with a black and white answer here. There are some cases that I could think you have a good point. On the other hand, there are also some cases where I believe the cable still needs to be there and able to go to a safe position. So let me just set we answer this live and let's move on. All right. I got a poll question. There's the first poll question coming up for today. I think we have two or three poll questions today. The role of the power supply for an instrument devices in a de-energized to trip application. The reason is it's a reliability issue for that safety instrumented function. I don't know if you can launch the poll or not, Gabriele, or should I try to launch it here? It's here.
No, I launch it.
Okay, good. Now, okay. Second, B, is it the availability issue for that safety instrumented function? Answer C can be both a reliability and a availability issue for that SIF. And that was closely answered with that fire resistant cable. Answer D is irrelevant for the de-energized to trip application, like some people may believe. And answer E, none of the above. So please give us some of your thoughts on that poll question. I need to have at least, oh, okay, now more answers are coming in. I almost said I need to have 70% of the answers from people coming in.
Close.
It's coming in. We need one or two more clicks, I think. All right. I think we do well. There's no one asleep yet, so it's good.
So I can close it.
You can
share the results.
All right. So we have some people said it is a reliability issue for that safety element function, and that is of course correct, because a reliability issue in the sense of that your power needs to be reliable, needs to be trustable, needs to have a certain accuracy of, let's say, 2% as an example. But it's also an availability issue for some of the SIFs, as you can imagine. So answer C can be both reliability and availability. And we will talk about the role of a power supply later on here in your safety instrument function, which we also refer to a separate independent a webinar from GMI. And then C, is irrelevant for de-energized to trip application? Unfortunately not. And I will first talk about this answer D. It is irrelevant. I will give you a real example that happened in the field on an offshore platform somewhere in Europe. There was a overcurrent in a safety power supply that was damaging some final elements. So when the safety loops were triggered to go to a safe state, the safety loops did not work anymore because of that power supply. So it is irrelevant for de-energize. I don't believe so, since some items in a power supply can also damage your instrumentation. And we need to be sure that the instrumentation will have power enough, also not have too much power or current enough, or also not too much current. So items needs to be monitored. And that is why we will talk in a minute about some diagnostic-based power supplies, like also, or power converters, like also GMI have on their portfolio. All right, we stop sharing this, and I'm trying to go back into the slides. Here we go. During normal process conditions, that means if your process is in a steady condition. I see that we have some questions coming in. Oh no, that is done. All right, so it's gone. sorry. So for normal process condition, where there is no reason to initiate your trip in your safety function, every subsystem is failure-free and is working as per requirements. So assume there is no failure in your individual subsystems. Everything is working or can work as or function as designed requirements. If you look on the subsystem for the power supply, as we mentioned before, a power supply can also play a very vital role, even in a de-energized to trip application. Like things like, why do we call it a reliable power supply or power converter? The accuracy is one, but the undervoltage, assume that you need a certain voltage, minimum voltage on your instruments. If your voltage would drop below that, maybe some instruments actually will not function the way they should, right? Overvoltage, well, overvoltage, as we already mentioned, an overvoltage can also have some damage on some electronic, let's say, parts, or maybe some electrical parts inside that subsystem. That is why if you go into the 61508, which is not really for end users, that is more for the manufacturers like GMI. If you would talk to the hardware developers from GM International, they will use the IC 61508, which is the leading standard for functional safety for EEPES systems. The abbreviation stands for electrical systems, electronic components in that subsystem, or something that can be programmed in terms of a programmable electronical safety related system. So when the hardware design or the hardware developer try to design a system safe, things they have to consider is also called the diagnostic, let's say, items that they need to protect their equipment against latch up or high inrush current, against overcurrent, and we are talking here about the techniques that they will use to measure the effectiveness of how can they actually detect that certain failures should stop their equipment from working safely. And a whole part of the diagnostics can also be built onto a safety power supply. And I had some discussions before with people, why do we need a SIL power supply versus a non-SIL power supply? Because they both provide the power. And that's 100% correct. They are identical. The only thing which is different is a normal power supply with no SIL integrity prediction will not be able to diagnose the items like here in this case has been explained for things like high inrush current or latch up, etc. Availability is another point. We have built systems for 50 years. We typically used power supplies where we use a diode bridge in the back of the power supply enabled to build some redundancy for doing some load sharing. So load sharing would be that if one power supply is not available and you may have a modular rack design, maybe the other power supply can still keep as a backup the power available for your instruments. And again, if you want to go more in depth about the topic, why don't you go to the YouTube channel from GM International, as Gabriela was already mentioning. Every webinar is recorded, and you will see they have multiple times the same webinars. But I would recommend to listen to different webinars, because if it is me in the webinar, I can never talk about the things twice in the same fashion. I'm always talking about different things. So if you want to hear different views on the topics, why don't you look into more of one webinar? Last topic is the instrument there. Well, as you can all imagine, the instrument there also needs to be reliable, and a reliable instrument there would be accurate, would be free from contaminants, such as, for instance, there would be some moisture. That is why you will have some instrument there goes through dryers enabled for providing, or let's say not providing, enabled to trying to limit that any moisture would go into your instruments that potentially would damage some of your instrumentation, etc. Oops. Now, if you think about how do we now execute and achieve our safety function itself, once your process value in your field transmitter is measuring a certain value, that was set in your logic solver to be your trip interlock activation, the safety PLC will need to start the process to de-energize the digital output. Now, to de-energize something, to remove the power from something, is a lot easier, it's not rocket science, than turn on the power. In other words, if I need to open a contact and I'm putting multiple contacts, I have seen a system like 10 different, let's say, normally open contacts were all in series with each other, in the hope that one of them would be able to go open. In other words, it was a system with a very high diagnostic-based digital output module from a safety PLC manufacturer. And if something would go wrong in their diagnostic measurements feedback, they would actually be able to open, first of all, the individual channel of the digital output module. If that would not work, then they would turn off the entire module. If that would not work, then they would turn off the entire power to the chassis. If that still would not work, then they would down the entire safety PLC. So in other words, diagnostic-based in feature, or let's say in connection with watchdog timers on microprocessor-based systems, is typically sending out a signal. If the signal that is fed back into the watchdog timer is equivalent to whatever, let's say, action they were sending out into the field, they will keep the power on. Opposite, when the output was sent from the digital output channel to go off and they still measure some power at the end of the terminal strip of their system, they know something is wrong. It can be an I/O bus problem, it can be digital output frozen, or whatever could be the reason. That is why they have multiple ways, independent ways, to go to shutdown. The digital output channel will de-energize the safety interposion relay by opening the load. That's what we used to call the normally open contact principle. And then the solenoid will have to de-energize the coil of the solenoid, enable to vent the instrument there. Now, instrument there, it all depends on which side of the globe you are living. But I give an example. I was on a specific plant where it was pretty cold outside and the vents were freezing up during the night. That means if you were de-energizing one of your solenoids during the night, potentially your vent would be frozen up and would not be able to vent the air. So the safety function would not be achieved. So those are kind of things that you have to think of. Opposite, I was on the other side of the globe and I was in south of Texas. And this engineer in the field, he was talking about an animal or an insect called a mud dauber. And I thought, like, what does a mud dauber have to do with my safety function? And I said, because I am from Europe, I probably do not know what you actually mean with a mud dauber. He explained me it's a small insect building, a nest to put the eggs in, and the nest is made out of mud. And the mud, they typically put it in a very small hole. So all the vents on all the valves on that side, they need to have a mud dauber screen. So those are all the kind of things we have to think of. We say, oh, it's a de-energized. We just remove the power and the item will go to safe state. Not necessarily. There may be some environment conditions that you have to consider also in terms to go to a safe state. And the last one here, suppose the shutdown valve is a spring return valve. As we already mentioned, the spring torque should have power enough to go into a safe position. Now, we will focus on the problem area, which is at the final elements site. So the modern safety PLCs, as I already mentioned, working with diagnostic, with watchdog, that's all the easy part. Then the interposing relays from GMI. Some of the relays are quite smart, so I call them almost smart relays. It's not the same as a smart transmitter, but that means that they have some diagnostic-based relays. They have even relays with some line monitoring. That means that even when the load on the field is off, they can still monitor the condition of the line, like for earth faults, etc. So again, there is a specific webinar on real applications for relays with line and load monitoring, which I'm not a specialist from GM International. That's why we have Gabriele here. If there would be a question, I'm sure that he can help you to answer that. I took here the picture of that smart interposion relay from GM International. And as you can see, it is more than just opening a contact. There's also some feature in there where they will see the condition of the, let's say, the input of the signal that goes into the interposing relay. With the diagnostics, they will also monitor more than just the output and also more than just the line or the load of the line. They can also look into the internal, let's say, healthy condition of that safety relay, and I can fit this back into some communication, like into a Modbus communication, and able to fit that back into your control platform. Here they give the, I'm just trying to think what the slide is talking about. Okay, here they give the example of the interposition relay where the load is on versus the load is off. So that's what I was mentioning. If the load is off, they can also look at short circuit or at a earth leakage that they could actually diagnose and fit this back into your system. I took here the courtesy of a system that was a company that used to exist in the Houston area. But I know that my friend has retired. The company is also closed. It used to be called SafePlex, but he built a application. He even got it approved by TÜV Rheinland for SIL 3. And basically what they did was for a very large multinational chemical plant in Asia. And they were building this stainless steel box here. And in the box were 4 solenoids. You had 2 manifolds here. You had 2 block and bleeds on both sides. And they put a relay, sorry, they put a PLC in there to do continuously block and bleed to replace this one single solenoid. So basically, the configuration was being recognized as a 2 out of 4 with some diagnostics built into that PLC. They had, in this 4 solenoids, they had 4 pressure measurements. So internally, they were doing continuously block and bleed. And the benefit of this box would be you do your instrument air in, instrument air out. There was no need for doing proof testing of this one single solenoid, as it was done automatically in terms of the configuration. But that is how complex certain installation will go in able to make sure they can remove the power, they can remove the instrument there in this case, and able to go to a safe position. And last but not least, we are looking at the final element. And if the reason why I'm saying you need to look at more than one webinar is because the webinar that we have done before, I think is the 3rd time over the last 4 or 5 years, we're doing the same topic, de-energized trip. In the meantime, in August 2024, that was end of last year, we finally got a new functional safety standard, which has been referred to here as EN 17955. So the European norm 17,955. Title of the standard is Industrial Valves, Functional Safety of Safety-Related Automated Valves. And you may see here, I give you a link in that webinar. And the link is to a website from Estonia. And now you're probably totally confused now. Why do I give a link to an Estonian website? Well, I'm trying to help the industry to give you a reliable, legal link to the standard, which doesn't cost you the same amount of money that you can find through other channels on the market. For instance, if you would go to the European norm site, I give you a reference, it would be around 250 to 300 euros for the standard. If you go to the Estonian website, which is a legal website also, you will pay as much as 33 euros. So it's about 1/10 of the price that you would go to buy the standard officially. And the reason why I'm trying to promote this is in all these years that I'm doing functional safety in, let's say, the process industry, we have been struggling for more than 30 years, always about the final elements. Because the final elements are classically subsystems from different vendors. You may get an actuator from vendor A, you may get your positioner from vendor B, and you may get, let's say, your ball valve or your gate valve from vendor C. And the question is, how do you combine all those vendor equipment and how do you predict how reliable they are? Because it goes without saying, the actuator vendor has nothing to do with the ball valve vendor, as an example. That means that they will take no reliability or no responsibility for each other's quality. But you as a safety engineer that wants to use this into a SIL 1 or SIL 2 loop, how do you start with that? And of course, we then have some databases, we have some predictions, we take some generic data. But finally, after all these years, we have a standard out trying to help the industry. So if you have any mechanical specialist listening into this webinar here, that standard will give you some ins and outs on functional safety for no longer have to use 61508. They don't try to replace the fundamental framework of the 61508 standard, but we all knew in the past that based on some paper that vendors were giving, the majority of all the paper was based only on a 61508 assessment. And a 61508 assessment for electrical, and programmable electronic system on a mechanical actuator doesn't really make sense. In other words, they were doing mechanical FMEA on that specific equipment, and based on the framework, they were trying to predict the availability. Well, now with the standard, in the hope with the standard, it will be more easier for those specialists to predict the availability of such a shutdown system. Right, as per 61511, which hardware concept can be still suitable or compatible? And we have 4 potential answers this time. As per 61511, answer A, de-energized to trip is prevention protection layer. Then we have B, energized to activate. It's your mitigation protection layer. Then we have answer C, which is both A and B. So that's an easy one. Or answer D, none of the above. And again, we would appreciate if you get 70% answers on this poll question also. Okay, we're getting there.
Yes.
Okay, Gabriele, I think we have reached our target.
And share the results.
Okay, so as you can see on the results, I was just in the meantime looking at some participant. Okay, right. So people who said de-energized to trip is, of course, the majority of all the safety loops will be indeed de-energized to trip. Energized to activate, you can see that there was, well, at least here in this case, there is a minority who is saying energized to activate. Both A and B is, of course, the correct answer, as you can see it also on the majority of the votes here on that poll question. Now, a misconcept or a misunderstanding from the edition 1 61511 standard was that the IEC 1611 was only written for the prevention layers. That is where your SAS layer is really sitting into the prevention. And some people were saying, well, fire and gas is actually not belonging into the 61511 because it's a mitigation layer. That was not 100% wrong, because the mitigation layer, as you will see it in the layer of protection analysis, let's say principles, and mitigation is already coming after your prevention layers. Now, the edition 2, 61511, for the IEC part has written a technical report number 4, which was given out somewhere in 2020 by memory. And that technical report 4 was saying a misconception from the industry was thinking that a energized to activate, in other words, things like a fire and gas system, does not belong in the 61511 and does not have to be built reliable, which is of course not 100% correct. What did technical report 4 give us now? They say that minimum a reliable mitigation layer should be built with the same integrity to the level of a SIL 1. Now, I would like to give some comments on that. That a fire and gas sensor, with or without a SIL certificate, or with or without a SIL suitable, let's say, evidence, is not really relevant if the sensor mapping is not correctly done. And I give you 2 examples. Assume that you have here a sensor, which is my left-hand side, which has a SIL prediction on it. And the sensor is actually pointing out, but the wind is blowing the gas to the other side. That means, although it has been a SIL predicted reliable sensor, since the mapping in this particular case position is not in favor of smelling the gas concentration because the wind is blowing the cloud to the other side. But luckily on the other side, which is my right-hand side now, on the other side, we have a sensor with no sill prediction at all. But the sensor is pointed out to the right direction where the gas concentration is measured. Then I'm asking the customer, which one do you prefer? Do you prefer a sill one where the mapping is not done correctly? Or do you prefer a non-sill prediction where the mapping is actually done more accurate? In other words, the fire and gas sensor mapping for me is a lot more to think of than a sill number on that device. Same with the manual call point. If you have a manual call point between me and the fire in front of me, well, if I can actually not reach the manual call point with a sill number on that, I rather push the button with no sill that is just next to me because I don't have to run through the fire. So again, sill prediction, I fully agree. Once a signal has been recognized, we need to have a reliable instrument to provide the reliable instrumentation, let's say, value to the logic solver, but the logic solver still have to be able to activate the safety function. And that brings us to the next topic for energize to activate. Energize to activate, as already mentioned, here we need to have the energy. That's why I also opened here the webinar today with the example from Spain and Portugal. Well, if you have an energize to activate functionality in Spain and Portugal during the day that they lost the power, well, I'm pretty sure they cannot do anything because they have no power. So the energy is part of your safety function here. So again, it must be reliable. Again, it must be accurate. Again, we need to think about the over current and the over voltage, etc. But here, the energy is the real essence of your safety functionality. ETA, or energize to activate, is never fail safe. If you think about that, how often have you seen a spirit strip on an energized to activate system? How often have you seen in your industry or in your process plant or in your plant itself, have you seen the loose system starting for no reason? Most likely not so often, because we're going to build the redundancy in a certain fashion that we don't want to have this happening if it doesn't need to happen. Opposite, how often have you seen a spirit strip on a de-energized to trip functionality? And I'm pretty sure your production people have often seen that the safety system has carried out the safety function with no reason. That's why we call it the nuisance strip or a spirit strip, because let's say the nature of the loop is built when the power is gone, it goes to the safe state. And that's, again, that's a lot easier to achieve than here with the energize to activate, because here we need the power, we need the energy, we need the instrument there to do things. So power in this type of safety loop is the availability itself. And common examples, for instance, would be, as already mentioned, the loose system, fire and gas, fire suppression system, foam systems, etc., etc. Since in normal operations, in normal conditions, the loop has no power, another thing we have to think about is your monitoring of your line. That's what we call the line monitoring or the load monitoring on the digital output channels to diagnose the effectiveness of the line itself. In other words, if I would cut the cable on an energized to activate loop, and there is no line monitoring or no diagnostic being able to detect this or to able to measure or recognize that, maybe you would like to power on the line and the line will not be able to power because the line is gone. And that's why we have this special feature. Typically, in the old days, we use an end of line resistor, end of the line. We had a small milliamp signal going into the line to measure some milliamps to prove that the line is still there, in the hope that if we will power up the line will be still there and able to provide the power to my final element. But as I was mentioning before, like in Spain and Portugal, how do you turn on the power when you have an internal failure in your safety instrument system and there is no maybe power available? Or maybe when your digital output module has an internal failure, how can you actually move the power to go on a power on condition for your final element? Now, often What we do see in the industry is, to make it simple, that they will, for instance, go by a de-energized to trip functionality. They will invert it with an inverse interposing relay, like the one we will show in a minute from GM International also. And they will have the same concept throughout the entire site, even for energized to activate as for de-energized to trip. But if you have one safety PLC vendor functionality configurable box in front of you, and you have one backplane, and they're mixing de-energized to trip modules, which are the majority of the modules, with the energized to activates, which are typically the minority in your system. So let's say, assume that you have a fire and gas application also in the same system. If you have one commonality, one common backplane, how will you move the power on if you have an internal failure on, for instance, that system? Those are the items that needs potentially some more, let's say, engineering ideas about it on how to achieve that. Safety PLCs, digital output cards with line monitoring, often have not the necessary power current available, so you go to an interposing relay. If you take an interposing relay with no line monitoring, you're losing that functionality. That is why the line monitoring functionality in a interposing relay can take over that functionality to monitor the line. The signals can be fed back into your control system to actually tell you what is the condition of the line, so you don't have to lose that by using an interposing relay would not have that functionality. That's here the relay. That is the direct relay, as they call it here in GM International. That's the energized to activate. So we have a normally open contact. So it's a one-to-one input in, output out. That means if you power on the input, the outputs will be powered with a certain fashion. As you can see, it's more than one normally open contact. The configuration is made as such that they will make sure they can remove the power if the input will lose the power as an input condition. Opposite, if you want to inverse the logic, that means a 1 in will be a 0 out, or a 0 in will be a 1 out. So it's just the inverse logic with a de-energized relay input to energize the load via a normally close contact. Conclusion. The concept itself is not difficult. It's just the way we're going to engineer it. We're going to actually build our safety loops and able to go to the right condition if we need it. And the energized to trip is the only fail-safe. Energized to activate can never be fail-safe, because there we have to think about how we will provide the power to our mitigation layer. Last bullet here, or the second last bullet, frequently taught that de-energized to trip does not need anything more than, we are removing the power and we can go to a safe condition. Well, we have given you, I think, plenty examples to think about, that the power supply also needs to be reliable, also needs to be diagnosed, etc. And as I said before, the report number 4, and it was in 2020, it was in February 2020, was released, report number 4, saying that also for the protection layers, like mitigation layers, needs to have a certain reliability equivalent to a SIL 1. As Gabriele was mentioning, and I saw that there's a question coming in, if you use an inverse option, then could we say that ETA can be fail-safe to the limit of the safety relay? I would say yes. Opposite, to the final elements, I can think about some conditions where you cannot say they are fail-safe. So it depends on how it is engineered. So again, if we use an inverse option, that you use de-energized to trip to the logic solver, and you're going to inverse a signal to power on the output to the final element. Again, the same question. If your power is not available, you will not be able to go to a fail-safe condition. So we are remaining with the same problem or dilemma there. Okay, so this is also answered to this. So on the consultancy, we are doing mainly consultancy on functional safety management. We can also do it during the design phases. We are helping currently an EPC contractor on some of their safety requirement specification. Another example, we were involved in the layer of protection analysis. And with one of the biggest projects in Europe currently today, it's a billion-word project. We are being assigned to do the functional safety assessment. So we have just done last week assessment number 2 on the life cycle. We're also more involved in the cyber security for the operational technology, the OT security with the 62443. Plus, we can also provide you the training for both. We are doing the TOV Rhineland. We are still the license. We are still a course provider with a license for TOV Rhineland courses, both on functional safety, but also for cybersecurity. And then, last but not least, for those who are not familiar yet with the book is out in the 5th edition, which is pretty new. I think it was printed in February. We have been giving out some books already. And in that latest book, the 5th edition, I managed to write a new chapter called chapter number 10, which is the functional safety management. That's the book edition number 5. Now, there were some questions coming in before. That means when you did your registration, some of you could not wait to give us some questions, which is good. That means we can prepare. Now, I wish I would find it somewhere in my slides. Okay, let me look for it because it was opened this morning, but maybe something went wrong. Okay. Question and answer should be this one. I'm trying to share the right one, so give me a few clicks. Is that the one I'm trying to share? I think it is. I have a feeling something is going. Can you see the question and answer? All right. I see that Gabriele is giving me the mark. Good. So in the questions, first question that we got from some of you who did the registration. What are the typical pitfalls and misunderstandings you have found when reviewing your clients, end users, and or integrators projects with regard to the selection of de-energized to trip versus energized to activate? Well, we are trying to be neutral here, of course, in our findings for not targeting one of the ones that we found quite remarkable. So I give you here a list to put some thoughts of. In the fail-safe principle, it could be ignored in the terms of loss of power, not treated as critical failure risk. Again, some engineers will jump too quickly in the conclusion it's a de-energized to trip, so we don't need power. And as I was mentioning before, in certain cases, for certain loops, for certain safety application, you may need power for let's say, a limited number of time for you in able to go to the safe position. Some engineers will go even further and they will do some failure analysis. They will take one of these methods called FMEA, failure model effect analysis. But then again, a weak failure analysis in the sense that during an analysis on a de-energized to trip application, the power itself can actually bring you into a additional, let's say, risk criteria when the power is not accurate available, when the power is maybe in an under voltage condition. So those are kind of items that we would recommend that also need to be considered if you would do some analysis on the, let's say, the potential power availability. Then the false confidence in redundancy, often in the old days, because they are using redundant power supply, they say, well, if one is not working, maybe the other one will be working. But then some people would maybe forget the common mode effects on your system. Common modes for us are again systematic failures, are purely design failures. But the common mode can be that if the common platform that even, let's say you have redundant power supplies, but they have to go into the field. If the common mode, and I give the example, I'm just reminding, I was on one of the webinars where I gave the example with some fire trucks, and I was showing the end user. They were using 4 fire trucks, and they had 2 bridges to cross the channel. And I asked him in terms of availability, I said, well, you have 4 fire trucks, but you are limited to using those 2 bridges. If one bridge is going open and those 4 fire trucks has to go over one bridge, that is your commonality, that you use this one bridge to actually go to kill the fire. So in other words, if you have a safety PLC vendor and they are bragging about their 2 out of 4 systems and they're going over 2 IO buses, and you're losing one IO bus, your common ground is this one single IO bus enabled for you to go to the field to do your functionality. So in other words, try to make it simple. Think about what are my commonality enabled for us, even when we have redundancy. What is my commonality limitation that will bring me down in my availability? Not considering reliable diagnostic-based power converter supplies. Well, this offshore platform incident in the field that was actually having this damaged instruments because of not using a reliable power supply. It is because of this one end user that GM International years ago went into a development of building reliable power converters. And then also the maintenance overload. If you go to the energized to activate safety loops, they need also dedicated, let's say, proof test coverage and proof test functionality activities. And it could be an overload also that was not considered during the design. The 65011, if you look into some very specific details, and I took here clause 11. Clause 11 sits in your design and engineering details from the normative part 1. That's normative part 1. And if you go to clause 11.2.11, for any SIS device that on loss of utility, utility can be electrical power, can be air, can be hydraulics, can be pneumatic, does not fail to the safe state, loss of utility and SIS circuit integrity shall be detected and alarmed. In example giving, they talked about an end-of-line monitoring, which we explained. They talked about supply pressure measurements, which we haven't explained, but that was shown in that box, which was a 2 out of 4 for this one solenoid for the instrument there. Hydraulic or pneumatic pressure monitoring and action taken according to 11.3. 11.3 is a system behavior fault that will say that how will your system behave when there is a fault being recognized and able to go to a safe state. Second question came in. How can we implement the logic control to work in both applications for de-energized to trip or energized to activate so that the user, I assume here the end user, can configure his logic as per application? Well, basically that is what we already explained, but I just explain it again, or I just repeat it again. During the webinar, we showed you that if you have a de-energized to trip logic solver for everything, and you're going to invert it with that relay, which is mentioned here. That's the inverse relay, which is, I think I missed a number here on that. It should be 9.7, I think, right? So make sure that we correct this before we send this out to the people. And apologies, I made a quick mistake. We call that a systematic mistake, but I recognize it here because this morning before we started, Gabriele explained me it's the 5. No, he said it's the 9.7 relay, and that is why I recognized should be here a 7 at the end of this number. So coming back, you have a de-energized to trip digital output, removing the power to go to safe condition. In normal condition, you can actually copy that to interface the interposing relay with the 9.6 model. That's a 1-to-1 into out, or you can inverse again with the 9.7. So that should be 9.7 reading here to go from a 0 into a 1 logic. This approach would actually simplify the engineering all the way to the interposing relays. But as this one, let's say, attendee was asking me the question, it would not be still called fail-safe condition for the final elements, because the final element still needs to have power to go to a safe condition. Does this discussion mention and that engineer was probably mentioning the webinar discussion, mentioned power supplies that must be reset after the restoration of power. Well, I was a bit puzzled with the question, and I focused here on the word reset, and I may be wrong, but if I'm reading the question again, I'm thinking of the engineer was asking me the question, when the power supply is losing the power, or the power converter is losing the power, and the power comes back on, do we need to reset? And I was focusing on the word reset because reset for years, well, for 21 years, since the year 2004, that's the edition 1 of the SIG 1511, was clearly stating that every single safety loop that went to safe state shall need a reset unless it is different defined in your safety requirement specification. That's what I'm answering here. Considering de-energized to trip by loss of power and or bringing your safety instrument function in a safe state, your SIS shall be designed in such a way that once it has placed the process in a safe state, the process shall remain in that safe state until a reset has been initiated, as I said, unless otherwise directed by the SRS. That is clause 11.2.7. So, in other words, if we are looking into a safety requirement specification for one safety loop as an example, and I'm looking to this definition of reset, and the safety requirement specification has used the word not applicable, then I can only assume that that safety loop in the field will need a reset. Opposite, if your safety requirement specification clearly mentions we do not need a reset, well, then you don't need a reset. But the question is it advisable or is it wise for you to let your safety function reactivate when the power comes back on? Or do you prefer to first push the reset button? And again, if I'm looking over the broader picture, it's of course advisable to have a reset on your safety functions. And the question from the engineer was here in relation to the power supply. There is no direct connection in the SIG 1511 to power supply reset. But in the broader picture of resetting a safety loop after the power, for instance, brought into a safe state, I would say look into this definition of 11.2.7 and provide a reset unless you decide in your safety requirement specification you do not need a reset on your safety loop. And the last one was already answered, so we can be quick on that one. Cell-rated power supplies is required for de-energized to trip application. Well, again, there is a specific webinar on why a normal power supply is not always a good idea to use on your safety loops. We mentioned that reliable in terms of the accuracy, the under voltage, the over voltage, the latch up and high in current, etc., is defined by 6.1508 part 2, which is the hardware section enabled to measure the effectiveness of techniques and measurements to check how reliable that power really is. So in other words, is it a must? No. Is it advisable? Yes. And that is what I can answer here on this last question. Webinars, there is a link here to the future webinars. Of course, this keeps on changing because the top webinar is the one we have just done here today. The next webinar is for intrinsically safe advantages and disadvantages versus traditional flameproof. That will be a webinar given by some other specialists from GM International, and there will be some more webinars coming up in the future. One last poll before we can finalize this webinar over here. Okay, so this is not deciding my my check or my invoice to GM International, because it's maybe free of charge for you listening to the webinar, but it's not free of charge for GMI to hire us to provide a quick topic like we typically do. So we always appreciate if people show us some gratitude on what do they find of our webinar. You know what, in all these years, Gabriele, I never had someone providing me poor or not in line with the expectation, because if I would have one, then I would actually send an email and I would actually ask them, can you please explain me how we can do it better?
Yeah, right. That's true. Yeah, sometimes it's better to have a negative feedback so you know where you can improve. Yeah.
Exactly. All right. Well, thank you again for everyone. So we can probably share the results.
Yes.
So thank you for everyone that listening into this webinar yet again. And I'm sure that we will have some more coming up in the future. Let us find a few other topics. I sometimes believe the easier topics, the more people are willing to register for the webinar. So let us look for something for the future on functional safety. Thank you again. Thank you, Gabriele. Thank you to everyone. Have a lovely day. Keep it safe. And I hope the power will remains on in most of Europe today. You never know. All right. Thank you.
Thank you.
All right. We will stop sharing this and I stop sharing the slides and I will end this. All right, Gabriele. See you on the next one.
Thank you. Bye, Tino.
Bye.
Bye.